Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello students, welcome again to this TV learning program. My name is teacher Jamari. I hope you see that. And today lesson is for all of the senior 6C classes. And it is physics, you know that. I hope you are ready with the calculators so that now you can perform the calculations together with me. You sit comfortably in front of your TV screen, and then you follow and you enjoy physics. So we are still discussing on unit number 5, atomic nuclei and radioactive decay. And the lesson title of today is radiation detectors and decay law. This is what we have by today. So then we have the page book that you have to use is the book that you have from a REB website, okay? So this is page 137, and you go to 143 up to 145, and then you check on this lesson, but it is lesson number 9 that we are having. So, and these are the objectives that I want you to go with me throughout this lesson. Objective number 1 that I want you to be with up to the end of this lesson is to describe the functioning of radiation detectors. That is 1. I want you to be able to do that. Number 2, define and use the quantities activity and the decay constant. It means that you are able to define and you are even able to apply this into the question, right? So then another objective is to explain the decay law. In another word, you even need to do an example about that one, okay? So good. Now what we have after this is now these questions. You can ask yourself the questions that I have for you here. Now students, so here there is a question 1. How do we detect radioactivity and radiations? How can we detect this? And how can we know it's even there? How can we know that there is a presence of the radioactivity at a given place, or there is a radioactivity, or there is a radiation? Here is the answer. The answer is from the title. Do you remember the title of the lesson? It means that we can do all of these ones by use of, we can use the radiation detector just detector to find the presence of radiation. Now we can try to define what is this radiation detector, okay? So a radiation detector is a device. That is number 1. It is an instrument that is being used to tell you whether at that place there is radiation, that is about nuclear radiation, and there is an electromagnetic radiation, okay, or there is a light radiation. That is what we have by this device. Okay, so here we have the radiation detector is this is the device here. So for measuring nuclear radiation, okay, for measuring electromagnetic radiation, for measuring light radiation, this is a radiation detector. You have the good definition there now. Then we can go to the functioning of the device, the radiation detector. So maybe we take detector. So we can take one and what we call the gate mirror counter. So we can say this is the gate mirror counter, or we use this GM and then C. So it is sometimes it is a tube. We can say it as a tube. You understand that? That is a device number one. But before I have this functioning, so we have just the way it looks. So we have this is the device. As you see there, it has the screen. This screen, it is what we have as a lattimeter. On this one, we have the indication of the values. It is a lattimeter, of course. It gives the how much. So these radiations you are being exposed to. So, and then it has a speaker. The speaker is only to tell you whether there are this radiation. So here's the thing, that when there is a presence of the radiation at a given place, and then you bring closer this device here, so this one, and you bring it close to the place where you think the radiation they are going to appear, and the radiation will enter, and then there will be an indication here, and you can hear the clicks from the speaker of this device. Do you understand? So this is the device that we have. So let's now go to this. This is the work, how the gate mirror counter tube works. How can we explain the functioning principle of this gate mirror counter? So first of all, I want you now to understand what we have as the parts of this device, the simple. So we can simply try now to explain the structure, the part of the device, but where we think the radiations they are going out to enter, or they are going to ionize the gas, and then after to give a reading, but after you have these clicks telling you that there is this radiation, okay? So here we have the window, and we have the metal tube. As what you see, this is the central wire. Central wire right inside the tube. And then we have the low pressure gas. It is mainly the argon gas. So this is what we have, but it is into the tube. Do you understand that? So, and what you see, it is now connected to the high potential difference. That is the 450. It is that example that we are seeing here. So what we are saying as this functioning, but then we have one. So this one means that we have the tube that we are trying out to mean there. The tube, so in which there is a gas. And what does this gas is going out to help? Here's the thing. The diagram that we have is now is showing how the radiation will enter through the window, through this thin window. And then when it enters, they are going to ionize with a gas that is inside there. I hope you are following. They are going to do what? Good. They are going to ionize the gas. The ionization, you understand what it means. It is this way that there is going to be a presence of the charge or the charged particles inside the tube here. Okay? Remember, there is that gas. And after we have this ionization, what is there is a radiation enters the thin window and into the tube. And then next, there is going now to be this ionization of the gas. And this ionization that we have, there will be a collision of the gas. And the more collision is going now to produce more and more charges, more and more positive and negative charges And then this one will migrate up to the cathode and up to the anode. What do you think will migrate up to anode? So here is the example. So if the anode is here now, we have these alloys. The alloys here, the positive there, shows that we have the positive charges now migrating toward the cathode, and then the negatives, they are migrating toward the anode there. And then this flow. This flow means it is the presence of the current, and that current will create, will make the circuit be closed, and then you have a flow, the current, that is going out to make this lantmeter, indicating how much radiation you are being exposed to, and then, but with the help of this speaker, you will hear the clicks given out from that speaker. Of course, clear, then you think there is a presence of the radiation. So good. So this is what that's what we have there now. So it is here, we are saying that this current is detected by the speaker, giving a click sound telling you there is a danger, okay? You don't have now to get closer to this place. Hope you understand that. Good. Now the next one is what we call the photographic detector. So it is, this is number 2, photographic detector. This is another device, but this device is only, there is the chemical designed into the film. This is the film that we are saying, that I'm saying is this photographic film here. And it reacts, just make chemical designing into this film, reacts with the radiation to give the signal, let's say to give the signal or information, but on the monitor, here on the monitor. So monitor that I'm just like now saying is this kind of screen, or that is a monitor, and on which you may have now the value, and this value can tell you how much these radiations you are being exposed to. This is, let's say, 7, and then when it is a kind of watch. I hope you understand that. A kind of watch. Wearing that watch and then working at our place, and then there is this indication of the values, high values, then it means a high exposure of this radiation. So then here it is what I'm saying as the photographic detector. So they are mainly used by the workers to monitor the level of exposure of radiation. That is the thing. And what I've told you, that chemical in the film react to radiation to show the level of radiation the person is exposed to. But there is a disadvantage of this one. During the time that there is an explosion of the nuclear power plant, for example, and this one is not going out to tell you whether you are in danger, because you are, it is only showing that there is a presence of the radiation, but not to give you the information whether these radiations, they are harmful to your body. Do you understand? So that is the problem of this device. But again, there is a way of using the other different devices so that those other devices will tell you or will react to the radiations that may be harmful to you or to another one else. So here we have another one is what we call the cloud chamber. That is the last one that we are going now to explain. The last chamber, there are many, but I hope you can try to find So this is the cloud chamber. For this one, it uses the way of tracking. It is being used now to track the presence of the particles again. You see, always when we talk about the radiation detector, so there is that word coming now to tell you that is a device going now to tell you whether there are this radiation, there are this electromagnetic wave radiation, there are what we call the light radiation. So in a simple way, so the functioning principle is now going to depend on this device to another one. Okay, so now the device here, the diffusion cloud chamber is used to display the tracks of charged particles, I'm saying. It is the most useful for studying alpha particles because it has the strongest ionizing effect. That's what we have with this device. But again, I have what I want you to note down. You remember this ionizing effect of the different radiations? Do you remember them? Okay, so here we have a number one as the alpha particle. They are not easily diffracted and they have a strong ionizing effect as what we have defined there for this cloud chamber. Number two, what we have as beta, they have a weak ionizing effect. And the last one, they are what we have as the gamma particles. Okay, so then let's change to the point of radioactive decay. So what is the radioactive decay here? I hope you remember the definition. We have defined this one for so long into the other previous lesson. Radioactive decay. What is this? As it is there, it is a process in which atomic nucleus spontaneously loses energy to become another nucleus. This is what we have said. But again, you can recall this, or you can ask yourself, what is a decay? So the word here, decay. So what is that decay? Sometimes we use another word as the disintegration. Disintegrate. It means that to become another nucleus. So to become another nucleus, here it means that you have a nucleus that is becoming another nucleus, but after emitting a particle or a radiation. Radiation, we are saying, is that gamma particle. So here we have a diagram, okay? So just going to tell you again what we have. So the diagram here, you have a parent nucleid, and then it is becoming a daughter nucleid, then emitting what we are having as the particle. Here we have alpha particle, we have a beta particle, and then that is gamma radiation. Do you understand, the students? So we have defined this, we have explained these ones. So, but I'm trying now to, just to help you to remember what we have defined. Then let's go to the decay law. What is decay law? What is this? How can we explain it? What is this? Decay law, you can understand it after you have the explanation of what, the radioactive decay. Students, to have the nuclei, just the nucleids that I've shown you, to have this nucleid decaying, you know it is decaying from the other nucleids that you have. There are many, but it is not easy for this nucleid, maybe let's say number one nucleid, and there is another nucleid, number two, and there is another nucleid, number three. It is not easy. It is not by immediate to have this nucleid. Here we have a nucleid number one, and this is number two, then number three. You may have this nucleid one decaying, or you may have this one, or this one. But they are not going to decay just at the same time. One decay and then another decay. It means that this number 3 may decay, or number 1 may decay. In one word, I can now say that the radioactive decay is a random process. Do you understand? It is a random. So it is a random process. Then, as what we have said, it occurs spontaneous. It is a spontaneous. This is a spontaneous process. We have a 2. So it means that these 2 things, they are now combined now in order for us to understand really this law, the decay law. So here is what we are having. Here is what I'm saying, that radioactive decay is a spontaneous and random process. So the number of decays per second of a sample is called activity. This is what we call activity, and is measured in becquerel. So this is the unit of that. So what we call activity, that is A, is expressed into becquerel. That is becquerel. Okay? So this is the unit of activity. Remember, it is what we are saying as the number of decays per second. What does this tell you? Number of decay per second, you can have this one. It is the number of something then that is going out to decay per second. What is that? So it means that there is decay per second, which is going out to be the unit that we are saying as the 1 becquerel. In another word, activity A, it is equal to something that we have, and then times another thing that is expressed per unit of time. Do you understand that? So here we have, let's be quick, then we have this as the, just as the lambda times n, and then we need to understand what is this, the lambda, and what is this n. So just to save the time, here we have a frequently unit being used here is what we call a curie, whereby 1 curie is 3.7. The frequently used unit, for activity is curie. So this is, and it is now CI, whereby 1 curie equals to 3.7 times 10 power 10 here, and this is decay per second. So I hope that you see that. Again, so you can have this is going to give you the value of activity, but in decay per second. So let's have, just therefore we have, this is the unit that I've told you. The unit of activity is becquerel, whereby this becquerel is equal to 1 decay per second. So then, students, I hope then we can define what is this just decay law. Here we explain it as the number of nuclei decaying per second, and which is it is proportional to the total number of nuclei in a sample. So this is the definition of the decay law. So again, it is the number of nuclei decaying per second. So when we have this number of nuclei decaying per second, you can have it here. So from what we are saying as this unit, so you have this as the number of decaying. So this 1 decay. So if you have many, This is the number. So then per second, so this is giving you the law that we are saying. It is that activity, okay? So it is the activity, and then the formula is what we have there, lambda times the n. So then we can have this lambda as the decay constant. This is what we call the decay constant. And this lambda is what we call the probability of any given atom of that element decaying in 1 second. So this is the lambda. So now, students, let's have an example. So the example that I'm going now to give you is about, this unit here. So I hope that you have that. Okay. So then here we have this example. We have this example here. So this is the example. The activity of 5.0 times 10 power to 16 nuclei of radioisotope is 1.1 times 10 power 14 becquerel. Calculate the probability of the decay of the nucleus. So we can identify the data to correct this question. So we have the activity. This is A, which is equal to 5.0 times 10 power 16. And this is, there we have the activity of, this is N. Here we have N, and then we have activity equals to 1.1 times 10 power to 14 becquerel. And then you find lambda. So you apply the formula whereby you have this activity equals to lambda times N, and this gives the lambda equals to activity over N. So then let's substitute. So we find lambda equals to 1.1 times 10 power to 14 over 5.0 times 10 power 16. So then you have it into per second. This is second power minus 1. So can you calculate and then find the answer? So good. So you have the answer here. Let's calculate that. So we are having 1.1 times 10 power 14, and then over divided by 5.0 times 10 power 2, that is 16. Then I have to follow the parentheses, right? So I have the parentheses used. So this is the parenthesis that I have there. And then I find this is going out to be 2.2 times 10 power 2 minus 3. So then here it is 2.2 times 10 power 2 minus 3. Second, remember this is second power minus 1. Then the students, let's have a quick homework here. So we have a quick homework. The homework that I have for you is this one. So we have the device, and explain this device from the book you have, and then do the question here. It is very simple. Thank you for today's lesson. See you the next time. Bye-bye.